As always, if you haven't done so yet, please pause the video and attempt to solve the question on your own before listening on. In part A, we are asked to calculate the magnitude and direction of the electric field at this point right here. Now, the key to solving this question is that at this point, the electric field is produced by charges B and C only. Charge A itself will not produce an electric field at this point. So we really only have to perform two calculations, one for the electric field produced by charge B and the other for the electric field produced by charge C, because both of those charges are producing an electric field at this point. We know the electric field produced by a point charge is equal to the following expression on the right-hand side. Again, we're going to set this up two times, once for B and once for C. Notice that an absolute value is present in the equation, and with that in mind, we're going to go ahead and plug in the known values. Please recall that the charges are given in microcoulombs, so you'll have to multiply that by 10 to the minus 6 to convert it into the standard unit of coulombs. Also notice that the distance from charge C to A is 0.5 meters, as is the distance from charge B to A, because this is an equilateral triangle and all three sides are equivalent. So here are all the values plugged in, and if we compute that, we get the following answers. Notice the unit for electric field is newtons per coulomb. Now these represent the magnitudes, but they don't represent the directions, so we have to take that into consideration next. Notice that because charge C is negative, that its electric field would be pointing towards that negative charge, and that's because electric fields produced by negative charges always have a direction that points towards that negative charge. So we can label that electric field as EC. On the other hand, charge B is producing an electric field that points away from charge B, because positive charges produce electric fields that point away from that positive charge. So we could label an electric field that points in this direction EB. Now, because EB is pointing in both the x and y direction, we have to break it into components. So perhaps we could project a vector to the left here, and that would represent the x component, and then the y component would be projecting straight down. Note that the angle right here is 60 degrees because it's directly across from the angle marked 60 degrees here. So because this component, the x component, is adjacent to the 60-degree angle, we know that that's going to be EB times the cosine of the 60-degree angle. And then this vector, the y component, is opposite to the 60-degree angle, so that's going to be the EB times the sine of the 60-degree angle. Now that we have those two components, it's my preference to erase the resultant vector because we really only need to be working with the x and the y components in the next analysis. And in that analysis, we're going to be plugging in the components for electric field B and electric field C. Electric field C is pointing only in the x direction, so its y component is going to be 0. And so we can actually just use this value as the entire x component. Notice that because it's pointing to the right, it's a positive value. So we're just going to plug this in for the x component of electric field C. And then for electric field B, we're going to use the components that we found earlier. Notice that the x component is pointing to the left and the y component is down. Those are both considered to be negative directions. So when we plug those components in, we'll have to make a negative value for each. Next, what we want to do is sum both components. So we're going to have the total x component here and then the total y component here. So you can pick up your calculator and just add vertically the two x components and then add the y components as well. So with these total x and y components, what I prefer to do is to draw a new triangle. We're going to have the x component pointing to the right because it's positive, and then the y component is pointing down because it's negative. To find the resultant, which is marked in the red line here, we would just use Pythagorean theorem. And when you compute that resultant, you should get a value of approximately 222,402.6 newtons per coulomb. So that would be the magnitude of the resultant electric field. The direction will be this angle right here, and we can see that we have the opposite side labeled as well as the adjacent side labeled of this right triangle, so we can use the inverse tangent. And that angle comes out to approximately negative 88.6 degrees. Now your homework system might want you to express that as an angle that's counterclockwise from the positive x-axis. So if you superimpose a y and x-axis on our picture, we can see that the angle that the question is seeking is actually this angle marked right here. So we actually have to add this to 360 in order to get the value of this blue angle here. And if we do that, we get a value of approximately 271.3 degrees. So that would actually be the angle that's counterclockwise from the positive x-axis. For part B, how would the electric field at this point be affected if the charge there were doubled? Notice that we actually never factored in this charge into our calculation of the electric field here. So in fact, the electric field will not change if we double the charge at that point. So the answer to part B will be that it will not change. For part C, however, because the force acting on a charge is equal to the electric field times the magnitude of that charge, if we were to double the charge, then we would actually double the electric force acting on it. So although the electric field will not change, the electric force certainly will change. So the correct answer to part C would be yes. Thanks for taking the time to watch the video. If you liked it, please click the thumbs up icon and also subscribe to the channel. Remember, you can send your own question into this email address and I'll do my best to post a solution to it on YouTube.